Hi guys, so this purpose of this video is to spend a little bit of time more carefully distinguishing between little g uh, and big G. So little g, the acceleration of gravity at the surface of the Earth, this number that we've been using, in Newton's laws problems and stuff like that you've gotten quite familiar with, and in kinematics for that matter. Versus big G, which is this new quantity that we're working with, which is the gravitational constant. And this is equal to 6.67 times 10 to the minus 11 newtons meters squared per kilogram squared. And if you're new to this thing, it's easy to get these two numbers confused. Where this is 9.8 meters per second squared, the acceleration due to gravity at the surface of the Earth, versus this tiny number that we use in Newton's law of gravity. So I mentioned this in class that you can get little g from big G, but it wasn't particularly rigorous how we're doing that, and I want to look at that a little bit more carefully. So you can think of this as, imagine you're just, standing on the surface of the Earth, and we've been working with Earth has some mass and there's a radius to it. And we've been working with the force of gravity where we know that that is equal to, so we could look at the force of gravity on a person, say. And you know that it would be gmm over r squared. Now, if we wanted to find the acceleration due to gravity, remember F equals ma. The acceleration is going to be the force over the mass. So the acceleration due to gravity would be the force of gravity divided by the mass of the person, in this case. And that's what we know of as little g. And so if we do that, if we divide by that mass, that'll drop out. And we're left with g equaling this combination of stuff. So, and we can compute this. So this will be 6.67 times 10 to the minus 11. The mass of the Earth is this big number, 5.98 times 10 to the 24. Radius of the Earth squared. The radius of the Earth is 0.38 times 10 to the 6 meters. And we'll square that. And, we can estimate this really quick, and you'd see that this is basically 6 times 6, 10 to the negative 11 plus 10 to the, times 10 to the 24. So this would be times 10 to the 13 divided by basically 6 times 6 times 10 to the 12. So you can see, this is basically going to all cancel out, and you're left with something that's approximately 10 meters per second squared. And if we were to do this more carefully, we would get back the number that we know and love, 9.8 meters per second squared. So this is how you get little g out of big G. And the part of why I'm showing you this is because I wanted to make sure that, or head off the confusion, this doesn't have anything to do with the centripetal acceleration. This is just the force of gravity for that at that distance from the mass, from the Earth. Now you might think this seems kind of weird because, the Earth has volume, right? So what about, like, does that matter? And the short answer is no. And if you're interested in this issue, you can actually look into it in more detail in the book. But it's one thing that's interesting about this is that the mass of the Earth, for any spherical distribution like this, uh, It behaves as if it were concentrated at a point at the center. So even though the mass has, the Earth has volume and stuff, and it may seem weird that that wouldn't matter, it behaves mathematically as if it were all the entire mass of the Earth were at a point at the center, and that makes this picture of looking at you standing on the surface of the Earth maybe a little bit more consistent with what we've been talking about when we talk about satellites or something like that. And you can see there's an appendix actually in your book where you can prove this where they prove it for you. You prove by an integration problem. And it's kind of an interesting problem because you have to do it in 3 dimensions. And this is in Appendix D if you're so interested. Okay, so this is sort of a little bit more detail on the connection between little g and big G. And a couple other things that I wanted to mention with this is that, for example, you can modify little g by going to a different altitude. So, for example, the text talks about Mount Everest. So, kind of the same picture, but now imagine that you're on top of a little mountain that has some height. So Mount Everest is not a little mountain, but in this, relative to the radius of the Earth, it's a little, it's not very large. So if you look up the Mount Everest, you'd find that the height of it is about 8,000. What is it? Oh, I wrote it down here. Where did it go? 8,550 meters. And so we can compute this little g in the same manner, where now let's call it G Mount Everest would be big G, mass of the Earth. Now the radius would be the radius of the Earth plus that height, that quantity squared. So we can put that stuff in. The 5.98 times 10 to the 24. This will be 6.38 times 10 to the 6 plus this rather small number of 8,000 meters. So, and then we would square that. Now, you can tell, so the denominator is ever so slightly larger, so we know that little g that results from this is going to be ever so slightly smaller. And in fact, you'd get about 9.773 meters per second squared. So slightly, slightly less than our familiar 9.8 meters per second squared. You can think of this as being, like at sea level. And this makes sense because the radius is a little bit larger when you're at the top of Mount Everest. And this is due solely to the fact that you're a little bit farther away from the center of the Earth. So G changes a little bit with altitude. And then the one other detail that I wanted to mention is how does this relate to AR? So how does this relate to the centripetal acceleration? So you can think of this. So this is actually kind of a complicated question, but it's actually something that we can analyze. So how does this relate to AR? Uh, the short answer is that AR can modify this a little bit as well. So it depends actually where you are on the Earth. So as you know, I mean, the Earth is rotating around on its axis. If you were standing at the North Pole, say, uh, you're not experiencing any centripetal acceleration. So at the pole, there's no effect due to the centripetal acceleration. So in other words, if you look at this in terms of summing the forces, if you sum the forces in R, you would have the normal force, the Earth pushing you up. I'll draw this a little bit differently here. So at the pole, say, you have the force of gravity that's pulling you down, and then you would have the normal force that's pushing you up. And this is going to equal the mass times the radial acceleration, but there is no radial acceleration because at the pole you're not spinning. So in other words, this just tells you that the normal force, if you want to think of this as like the force that you would read on a scale, is just going to equal mg. Now this is different, however, if you're at the equator. So at the equator, there is an effect. So in this situation, draw our little cartoon here. And there's the normal force that's pushing you up. There's the force of gravity that's pushing you down. But now you're also feeling a centripetal acceleration due to the fact that you're spinning. Try and draw this. So it's going to point down towards the center of the Earth. In other words, you feel an AR here that you don't feel at the North Pole, or South Pole, or whatever. And so if we sum the forces in this situation, you have the normal force pointing out. You have the force of gravity pointing down, and that's going to equal the mass times the centripetal acceleration, where this is not zero anymore. In other words, you're experiencing a centripetal acceleration at the equator. And so we can solve for what that force would be. If you want to think of this as being like the force that you would register on like a scale if you were standing on a scale. And you can see this looks like mg. So we can substitute in what we know AR can be expressed as v squared over r. And you can think of, and then we can divide out the mass. So let's call this G prime. In other words, G prime is going to be the force on the scale divided by the mass. And so that would equal G minus V squared over R. Okay. And we can put in some numbers. We have to substitute in what V is in terms of T, but we know that V is just 2 pi R over T. So let's put that in. So G prime is going to be G minus 2 pi R, the radius of the Earth, over the period, quantity squared, divided by R. Okay. And you can see here we'll get a factor of r that's going to cancel, and we can put all our numbers in here. So in other words, this would be squared, t would be squared, but we would have just one factor of the radius of the Earth. We can put these numbers in. 4 pi squared, 6.386, and then we would have to put the period in terms of seconds again. And what you find is that this quantity, it's going to be small, 0.0337, so about 3%. But what this means is that G prime is less than G by about 0.0337. So in words, what this means is that the effective acceleration due to gravity at the equator is less than it would be at the North Pole by this factor. And in fact, it's about 3% less. Or 0.3% less. And this is why satellites and rockets and everything are launched from close to the equator, because the effective weight that they feel is a little bit less. And this is also relevant to our discussion about the validity of Newton's laws. So we've talked about, or we may have mentioned in class, this idea of, is the Earth an inertial reference frame? Because if you're spinning, you're feeling a centripetal acceleration. Well, this gives you a sense that the centripetal acceleration relative to the acceleration due to gravity at the surface of the Earth is a pretty small fraction. So 0.3% versus, or 0.03 versus about 10 meters per second squared is pretty small. And so, in other words, the centripetal acceleration part is a minor factor compared to the force of gravity that we feel at the surface of the Earth, and this means that we can safely treat the Earth as an inertial reference frame. Newton's laws are going to work, as we expect, to pretty high precision, and we don't have to worry too much about the fact that we're actually accelerating because we're spinning. So hopefully seeing these details about little g and big G and the centripetal acceleration, etc., helps a little bit with these ideas.